Alright guys, welcome everyone. Today we're going to be talking about Markov decision processes. It's a very core topic within AI. This is going to be a super short introduction just to the MDPs, and then we'll have other videos to cover the other elements of MDPs, okay? So in this video, we're only going to talk about what's the model and look at one example so we can understand the definition. But after that, we'll be talking about utility functions and solving them in other videos, okay? So first of all, let's understand what is the environment that we're operating in. We're trying to understand how to work with stochastic environments. That means these are probabilistic environments. How are they different from deterministic environment? Well, in a deterministic environment, if you do a certain action A in a state S, then you reliably reach the state S prime. But when you are in a stochastic environment, probabilistic environment, doing an action A in the state S could lead you to quite a few different states, and that might be represented also by accompanied by a transition probability of each of those states. So that's the underlying difference between the deterministic and the stochastic environment, and that's the environment that we are now operating in. Okay, and in this the whole concept is defined as a Markov decision process, which itself is defined as a set of states, a set of actions that you can do, and the transition function that we just referred to, which defines what is the probability that doing an action A in the state S actually leads you to S prime. So in other words, that's a probability of S prime given being in the state S and taking an action A. This transition function is also referred to as the model or the dynamics of the system. Besides the transition function, we're also given a reward function, which represents that if we start in state S and we do the action A and we arrive in state S prime, what is the reward that we get? The reward can be positive or negative. So if it's negative, maybe it's not reward at all. It can be referred to as a penalty. But within the context of MDPs, the function is referred to as reward. We're also given a start state and we're also given a terminal state. Going back to the reward function, sometimes the reward function may not need to be a function of all three things, S, A, S prime. Maybe it's just which state you're leaving from, and the reward function is constant irrespective of which state you enter. Or it could be it's just a function of the state that you're arriving into, S prime, or it could also just be constant. So in that case, that's the reward function. The terminal states that we are referring to, you can see two terminal states here on the top right and the next to the one below top right. Those are the two terminal states. So we can see that MDPs are essentially search problems. In a way, we're trying to find the best sequence of rewards here, but these are non-deterministic search problems, because when we take an action, we may not end up in the desired state. We may end up in a different state. So because these are non-deterministic search problems, we can certainly use the expect-max search that we have already covered in the past, and we can use that. However, we will have a different way to solve this. Okay, a better way to solve this. So let's further our understanding of this concept of the MDP, the Markov decision process, by looking at one toy problem, which is the most common toy problem for MDPs. It's called the grid world. In fact, so much so that many times people might even use these two terms interchangeably. But just so you know, grid world is just one toy problem that tries to explain and tries to help us understand the topic of Markov decision process. Markov decision processes themselves are extremely useful, but the grid world is a common toy problem for us to help us understand it. In this grid world, it's a maze-like problem. So it's kind of like a 2 by 3, in this case, a 3 by 4 matrix, any two-dimensional matrix. The agent lives in the grid, and the agent starts from the start state. It goes whichever direction it wants to go in, or it tries to go in that state. But there's a stochastic or a noisy movement. So that means sometimes when it tries to go this direction, the north direction, it may it may go in north direction with 80% probability. While in a different grid world it could be 60%, 40%, but whatever are the dynamics of that particular MDP, that action happens with that probability, and in 10% of chance it maybe goes right, the east direction, or 10% chance it goes west direction. Now if it does try to go west direction, if you see from this particular graphic here where the agent is right now, here if it does try to go north, and let's suppose with a 10% probability it ends up trying to go west, but there is no way to go west because this area is blocked off, then it will just stay where it is. These are the dynamics, the usual dynamics of the grid world. So essentially it starts from here, it might have a reward to go here, and it wants to get to one of the terminal states where it has this particular reward, and you also see that there's another terminal state which has a -1 reward. So if you want to maximize it, you start from the start state, then it's reasonable to assume that you'll have the agent go north here, hit this area and try to go east. And the fact that you came up with a path is because of your search, whether you use an expected max search or you use some other mechanism to search it. But that's grid world in a nutshell. Talking about the reward, there can be a small living reward each step. It can be positive, it can be negative. So maybe it gets a 0 reward, or it gets a -0.1 reward, or it gets a plus 0.1 reward. And then it wants to maximize its overall rewards here. That's what it wants to do. And for the time being, I've written maximize the sum of rewards, but maybe it's not exactly maximize sum of rewards, it's something close to it, which we will cover shortly as well. Okay. So let's just qualitatively see how do different rewards make the agent's policy or agent's direction a little bit different. Let's suppose that the terminal states are still given as they are, and the living reward is very, very small negative, it's -0.01. In that case, the agent will try to go this direction, pretty much like we discussed earlier, but you can see there's an interesting step here. In this particular state, the agent's kind of trying to go this way, which can best be described as sort of hitting your head in the wall. Why? Because it kind of thinks that, okay, if I keep going this way, eventually, because of the 10% noise, I will either go here and then go here. But if it does try to go this direction, then there's a 10% chance it might just end up in the negative state here. For that reason, the agent tries to go this way to the west here, even though there's a wall here, because it knows with a 10% probability, it'll eventually end up in this particular cell and it'll be very close to it. And because the living reward is so small, it's almost 0, a conservative path seems to be okay for it. Now, if the living reward is not so small, then it certainly wants to go this direction and takes a chance. Again, I'm only speaking qualitatively here. I'm not trying to prove to you here that with this particular reward system, this is what will happen. But one can imagine that yes, if the living reward is so small that it has time to wait, it can wait for this. But if it doesn't have time to wait, then it'll try to go this way. And similarly, if the living reward is even higher, negative, then you can see that even in this particular cell, it tries to take the short way because it does not have time to go this way, because it knows it will take time to go this way and it'll cost it some living reward anyway. So it makes this chance even over here. And when it becomes even more negative, it actually finds a -1 to be better than even going all this way. So it just even from here tries to go into the -1. Again, qualitatively, we can see that how having different rewards can change the agent's output. So then the question can be, why are we studying MDPs at all? Like we already discussed, it's a stochastic environment. We could just be using Expectimax, and we would be using Expectimax if MDPs were a rare problem. But the reality is that MDPs are so common that a solution involving them that is much faster than Expectimax search. Therefore, it just makes sense to apply this much faster method. So we use this faster method and we don't really use Expectimax for MDPs. When we keep hearing this term Markov decision process, what does the Markov really come from? Where does Markov come from? So Markov in general means that when you're given the present state, the future and past are independent. In other words, the future state just depends upon the present state, does not really depend upon the past state at all. In even other words, if whatever the knowledge is of the state is all embedded in the current state, we don't need to go into the past states at all to understand what will be the prediction for the future. The present state already has all the knowledge inside it, embedded inside it, that it can have the transition probability based on the present state. When we write it mathematically, we write it as follows, that the transition probability that in the next time slot will be at state S prime, if in the current time slot we're at st and we do this action, and in the past we were here in this particular state and we took that action, and in the past state we were in that state, is effectively the same as just knowing the current state and the current action. So this particular expression is equal to this expression. So that means that these items here do not play any role in the transition probability. So, and this is what we refer to as Markov, and this is named after Andrei Markov, who lived from late 19th to early 20th century. Okay, it's kind of like search, where the successor function could only depend upon the current state, not the history. Okay, so this is pretty much what I have. It's a very short introduction, what we have just covered. What are MDPs? What's a model? What's an example? And we will be continuing this lecture series with understanding the utility functions and then going into how to solve MDPs.